Shane, I'm ready when you guys are. Did you want me to do your camera?
I didn't even get it this time. All right, folks, why don't you settle on in if you want to grab another piece of pizza. Do so now. I'm going to introduce Mark officially in about a minute here. So.
Is that the method pop? Oh, you probably don't. Yeah, he was like really too much stuff on. Yeah, like he had a really bad, like it was some of the food actually was like so good. Yeah, it was a while back. My brother watches that for dinner. He was still sick, and he was like, "I'm gonna eat a little bit of popcorn. I'm going to eat so much popcorn." I'm like, "No."
Okay, why don't we get started? So if you could find a comfy spot. I know that as last time, we'll have some people coming in a little late, so we have some chairs a little better arranged to handle those folks this time. I got more pizza this time than last time, so we should have plenty of pizza. So, well, we're very lucky to have Mark Pepin here today from the University of Minnesota, who's taking time from his busy schedule to be with us today to talk about his experiments that he's working on, his experiences that he's gone through, and to answer questions. And so I just want to remind you guys that these are really meant to be interactive sort of experiences, so please, if you're not clear about something, if you have questions on something, go ahead and ask. Okay, and just sort of, that's all right with you, Mark? I'm guessing it is. So let's give Mark a round of applause. Welcome students from Irondale here and Mounds High School. So thank you very much again for coming.
Someone already found my first typo. I guess Irondale's one word, so sorry about that. It probably won't be the only typo, but there it is. So thanks for having me back. I did this last year for the first time. Apparently must not have been horrible. I'm back here. So first, let's see here. Before we start talking about physics, I just wanted to give you a brief, overview of kind of who I am and the kind of schooling process I took to get where I'm at today. So I'm actually native to the Twin Cities. I grew up just down the road in Roseville, so not too far away. Went to high school in St. Paul, actually, so I'm very familiar with the area. For college, I went to Creighton University. It's in Omaha, Nebraska. And I got bachelor degrees in physics and math, which is a common combination for physicists. You have to do about half a math major to get a physics major anyway, so it's very common to just expand and do both. And now I'm currently, this is now my 5th year in graduate school at the University of Minnesota. This is hopefully my last year. But you know, this number keeps getting bigger and I want to get out soon. So I study particle physics and cosmology, and that's kind of what I'm going to talk to you a bit about today. Alright, so here's just a little bit of an outline of the physics part of the talk. So I'm first going to kind of bring up, what is the big scientific question? What is the problem that me and my colleagues are trying to solve? And then I'll kind of talk about some of the solutions. There's quite a few out there, some more fanciful than others. And then this is kind of lead into, I am an experimental physicist, so I'm going to talk about the detectors we use to kind of help solve this problem. And this will kind of have a slight historical pictorial detour in it. And then I'll talk about my actual experiment, which is the super CDMS experiment, what we do, what we try to do, and I'll be honest, we probably won't get to results, because hopefully you guys will ask lots of questions. That's in there in case you guys are quiet and don't ask anything. Alright, so the main problem can be summed up in that when astronomers, physicists, they look out into space, they have these nice big telescopes like the Hubble Space Telescope, you've probably seen images of that, and they look out there and they say, hey look, there's a lot of cool stuff out there, there's galaxies, there's big clouds of gas, whatever, But the problem is then they can also try to compute how much gravity they see out there as well. Right? And the idea is that gravity should, to the best of our knowledge, should act like, well, what Sir Isaac Newton said it should act like. So this is kind of a 400-year-old idea that gravity should kind of have this relationship shown here, where you have the masses of two objects constant, and they go as 1 over the distance squared. So if they're further away, force of gravity is going to be smaller. Closer together, force of gravity is going to be greater. And this has pretty much held up for 400 years. The second most famous guy in physics, Albert Einstein, he adjusted this slightly about 100 years ago, but for the most part, this is, hasn't changed. So we think we know gravity pretty well. The two smartest guys in physics who's ever been, they both say this is right, and you know what, they're pretty close, as far as we can tell. Nothing's wrong. However, when people look out into space, they see that this isn't really what's happening. So someone first noticed that something fishy was going on about 85 years ago, 1933. Franz Zwicky, a Swiss astronomer, he looked out at this image over here. So this is a cluster of galaxies. It's probably hard to see from back there, but each one of these bright dots is actually a whole galaxy. And the idea is that Einstein says that if you have something here, shining light, something in the middle that's really massive, and us on the other side, that the light should bend as it goes by this thing in the middle. And so that's what, there's kind of like these arc circles that you can maybe make out here. And this is that the light is being bent by other galaxies. And this was a new prediction that Einstein had. People were still testing it. It sounded crazy then. Still sounds a little crazy now, but well, Einstein was right, like he usually is. And so Zwicky was looking at this picture, but he realized that if we want to bend this stuff as much as we're bending it, we need more stuff here than what we can actually see. So we can see a big galaxy there, but the galaxy is not big enough to cause the effect that he observed. So he kind of, raised his voice and said, hey, something looks weird. Well, it's 1933, and they say, hey, astronomy's hard, you probably made a mistake. And they left it there, and no one really thought about it for another 40 years. Until another physicist, Vera Rubin, a very good physicist, I think she was at MIT, she did another study where she was looking at spiral galaxies. And what she wanted to measure is how fast stars are going around the galaxy. And the idea is that if we kind of maybe think about the solar system, is that, well, according to Mr. Newton up here, the stuff closest to the sun, Mercury, it has a really strong gravitational force. It's going to go really fast. Stuff further away, I don't know, Neptune, Uranus, or if we still want to talk about Pluto, it's really far away, gravity is much weaker, it should go a lot slower. This is exactly what we see in the solar system. Planets closer to the sun go much faster than planets further away. And this is really kind of what should happen for a spiral galaxy too. You have a big bulb of crap in the middle. Further on it goes, kind of acts like the sun. So you expect to see this red curve that comes up and then goes down as you get further away. So the stuff way down here should be going really slow. And the problem was that Dr. Rubin looked at hundreds of these galaxies. And what she saw is instead of stuff on the furthest out going really slow, it kind of leveled off. And so stuff way, way on the edges of the galaxy was going just as fast as the stuff on the inside. And according to what we thought we knew about gravity, this galaxy should blow itself apart. The stuff on the way on the outside is going too fast, it should just fly away. But the galaxy's been spinning for a couple million years happily and just fine. So, and she did this very well done. It was a very nice study. It was hundreds of galaxies. There was no way people could ignore this at this point. They're like, okay, the Swiss guy 40 years ago, he must have been right. This is too good of evidence to ignore. So people started talking about it in the 70s, for real. And then it wasn't until maybe about a decade ago, there's another study, which is called the bullet cluster. And this is a kind of a complicated example, so I don't have time to really go into it. But this was kind of like very conclusive evidence that when people saw this, like, yes, maybe dark matter must be a thing, or something definitely has to be wrong. Because this was incredibly powerful evidence. Unfortunately, I can't really go into it. So this is kind of generally the big background of something's wrong with gravity, more or less. And so what solutions might there be? So people thought about this for a while. So let's kind of restate our problem. So the problem can pretty much be, we observe more gravity than matches the matter we see. Well, if we want to solve this, maybe let's break it into two parts. First, we say we observe more gravity. maybe the problem is with gravity itself. Maybe, as smart as they were, maybe Newton and Einstein didn't know everything. Maybe there's still some aspect of gravity that's wrong or incomplete. So that's one idea. The second idea is, well, you know, these two guys were really smart. Maybe let's trust them and say, well, maybe the problem is with the second part here. You know, matches the matter we see. Maybe we don't see all the matter. Maybe we look out there, we see a nice pretty galaxy, so maybe that's not it. You know, maybe there's more around this galaxy that we just are not seeing with our telescopes. And so people argue back and forth with this one for a while. At first, the first solution was really popular because they thought the idea that there's all this stuff that we can't see, that sounds crazy. But unfortunately, when you try to solve the gravity is wrong problem, you solve this issue, but then you make a whole slew of other ones. Like you break conservation of energy. This is a really bad thing. So you kind of have to, you solve one problem, but then you make a whole host of others. And so because of this reason, this first solution is really not popular anymore, at least at this point. Maybe it'll come back when someone has a brilliant idea. Who knows? But where we stand now, people don't think solution 1 is viable. So that says, okay, then solution 2 must be right. And so this is kind of the prevailing idea of what we call dark matter. And the idea is that there is some massive particle out there in all of space, pretty much, and it interacts with gravity. So this is how we see it. This corresponds to the matter part. It interacts gravitationally, but it does not interact with light. This is the dark part, obviously. So it doesn't interact with light. That's why our satellites don't see it. And so this is the general idea about dark matter, and maybe how this could solve the problem. And we've been studying this now for a couple decades. And if you think this sounds weird, the weirder part is there's a pie chart in the bottom left, and this is right now, kind of the physicist's best guess as to what the universe is made out of. And you probably can't see all the details, but the gist of it is that there's actually 5 times more dark matter than there is normal matter. So not only is there some stuff out there we can't see, there's a whole lot of stuff out there we can't see. More than all the stars combined, 5 times more. And so this is the right solution. This is a pretty revolutionary solution. And the stuff we know about the universe is just a tiny little sliver of what the universe is actually made of. Moving forward. All right, so the next obvious question is say, okay, if this right solution is that there's some other stuff out there, great. Well, what is it? We should be able to maybe think about this. We know a lot about what stuff is made of. So this table I have here is called the standard model of particle physics. So I don't know, maybe you might have seen this. Yes, no, some nods. So the idea is that these are kind of the most fundamental building blocks of nature that we know of. It's kind of in chemistry, you have a periodic table where the fundamental object is the elements. Well, this is just take that, break the elements apart, and go one step further. There's some familiar things on here. This E over here is an electron, so I use that in chemistry a lot. The stuff in purple are all quarks. Popular science writers love to talk about quarks, so you've probably heard that word thrown out there. The 2 here, the up and the down quark, they make up protons and neutrons. So pretty much all of our normal atoms are made up of these 3 guys here. And then there's some other stuff going on. These guys, we don't see them usually. But if this is all particles that everything in the universe is made out of, well, dark matter must be one of them. So let's see, which one could it be? So the first part of our dark matter is, well, it's dark. It can't interact with light. So all the guys I've circled here, all 10 of them, these guys all interact with light. So they cannot be dark matter. Let's cross them off. Okay, the next question is that the universe is old. It's about 14 billion years old. Dark matter is still happily floating out there. So in order to be dark matter, it has to be a particle that is going to live for 14 billion years. So all the guys I've circled here, these all live for like, thousandths of a second. So they are not going to live for 14 billion years. So they can't be dark matter. So let's cross them off. That leaves these 3 little guys in the corner. So these guys are called neutrinos. If you were here when Dominic came a couple weeks ago, he probably talked a lot about neutrinos. He studies these in detail. And at first glance, neutrinos are really nice. They don't interact with light. They are stable. They live a really, really long time. There's just one problem though. They are really, really light. So neutrinos were first thought up of in like the 40s. And it wasn't until the early 2000s that we even realized these guys had a mass. So for 60 years, we happily thought they were massless and had zero mass. We now know that they have some mass, but it's just so incredibly small that there is not enough of these to cause all the gravity we're seeing. So maybe they're out there, they could have some effect, but for how strong of gravity we need, there's just not enough of them. So we can cross off neutrinos too. There's not enough of them out there. So this leaves us with a somewhat awkward problem. Everything we know that everything else is made out of cannot be dark matter. It's either a good thing or a bad thing. It's either a bad thing, we said, well, we're all crazy. Let's stop this idea now and go think of something better. Some people did that. They're still thinking of other things that could possibly be better. Could be a good thing, because you could just say, hey, we don't know everything. And this shouldn't surprise anyone. We're still doing science. There's still new stuff out there to discover. So this just says, dark matter's out there. It can't be anything we know about. So hey, there must be new physics. There must be some new particle out there that we haven't found yet that has to be dark matter. And this is kind of the approach that most people like to take. Is that, sure, who cares that we haven't found it yet? We didn't know it existed for until a couple of decades ago, so it could be something new. Why not? And well, theorists really like this idea. So let's just say there could be new physics out there. This is kind of the solution we're going to go with. It's at least the most popular solution in the physics community. And one kind of saving grace of this idea is that in our definition of dark matter, we said it couldn't interact with light, only interacts with gravity. We didn't say anything about the weak nuclear force. So this is kind of an obscure force. There's 4 forces in nature, and the weak force is one that doesn't get talked about a lot, even though it's very interesting from a science perspective. And the best way to think about the weak nuclear force is it's what causes radioactive decay. So it's it does happen all the time. Anytime there's radioactive decay, like PET scanners at hospitals, example they use this. So we didn't say anything about that, and so people assume that maybe dark matter, in addition to acting with gravity, could also interact with this fourth weak force, the weak nuclear force. And so because people like coming up with acronyms, the popular idea is this new particle is going to be a weakly interacting, so weak via the weak force, and because it's weak, massive particle. So a WIMP, also because it's weak, so we call it a WIMP. Someone probably had a great laugh when they thought of that the first time. This is the favorite particle type out there. You can get this from any number of theories. It's actually not just one theory. And kind of each theory that gives you a WIMP is kind of more creative and fanciful than the last. They involve things like extra dimensions. That sounds sci-fi-like. But people think about it. New forces we haven't found. There's a lot of these. As an example, here's a table where each one of these is a different theory for some new particle that could be dark matter. The checks and the crosses is someone did a paper of, okay, there's all these ideas, let's see which ones are still viable. Has some of these been eliminated? But you get stuff like gravitinos, sneutrinos, Suzy Q balls, that's a fun one. Champs and wimpzillas. I mean, there's also machos, it's not on this list, but people like to come up with names. And the idea is that, well, maybe about half of them are still viable, half of them have since been ruled out since the idea was thought up of. But, I mean, the theorists, they go to town on coming up with ideas. It's their job is to come up with new ideas, and they like doing it. So we look for one of these. We don't, as me doing an experiment, I don't really care which one it is as long as it's there and I can see it. But lots of ideas. So let's move on to, well, let's assume one of these exists. Whether or not that's a good assumption, we'll maybe find out in 10 years. And how might we go about finding it? I do experiments, not theory, so how would I find it? So I'm going to kind of go a couple general ideas on how you can find these guys. So I have a little diagram here. We're going to have 4 particles. The SMs here stand for a standard model particle, let's say 2 protons. We have a proton and a proton. Time here goes from the left to the right. So you have 2 protons hanging out, say in the Large Hadron Collider in Europe. They get smashed into each other. Some sort of nebulous new physics that we're hoping to discover happens. And out pops 2 dark matter particles. That's what the DM is. This is the idea that maybe we could actually make dark matter in a lab. It's crazy, but they actually do this at the Large Hadron Collider in CERN in Europe. I'm sure you've heard the LHC at least thrown out. They had a big discovery last year. So this is one of the things that they're actively trying to do, is to see can they make dark matter in their experiment. All right, so that's one way to do it, actually make it. Let's kind of take the same diagram, but let's make time now go the other way. Now we start with 2 dark matter particles. Let's say they're hanging out in space. Why not? There's lots of dark matter in space. 2 guys floating around in space. They happen to bump into each other. Again, new physics happens. They interact, and out pops 2 regular particles. 2 photons, for example, would be a good thing. 2 neutrinos, maybe. And then we, being humans, we could maybe detect these 2 guys. We could go out and look for these extra gammas, and these extra neutrinos. And people do this too. There's a couple satellites in space. One of them is called the Fermi Gamma Ray Observatory. They look for this all the time too. They kind of look at all the sky and see, do we see extra photons? Maybe those extra photons came from dark matter. So people do this as well. It's hard to do. You have to put stuff into space, but none of this is really easy. So this still isn't actually what I do. So let's do this one more time. Same diagram. Time goes left to the right to the left. Well, let's make it go from the bottom to the top. So here we'll start with the standard model particle. An example here, let's just say we have an atom. So we have an atom sitting on Earth in, say, my experiment. Then we have a dark matter particle floating around. It's in space. It floats all over the place, and it wanders in and whacks into my atom. The atom shakes a bit, and then the dark matter floats off. So that's kind of atom, dark matter. They come in, stuff happens, and then the atom and the dark matter go on their merry way. And so this is called direct detection, because we're just sitting there waiting for dark matter to hit us. And this is the type of experiment that I actually work on. One of the difficult things, as I said, while we are sitting there waiting for dark matter to hit us, this could take a while. So this falls into a general particle physics category called a rare event search. So there's something out there that could happen, just the chance of it happening is really low. So you either have to have your detector and sit there for a long time, and by a long time I mean something like a couple years, and hope your rare event happens. The other way you can do this is have a much bigger experiment, so you have, say, more atoms, and then you don't have to wait quite so long because you have more target for stuff to happen in. And there's a couple other examples aside from dark matter. Neutrinos, double beta decay, and proton decay are kind of 2 other quintessential examples of this. So let's kind of go from there and kind of latch onto this proton decay. So protons are in all of our atoms. They're in the nucleus. And as far as we know, they live forever. However, back in the 80s, there were some really good theories that said, hey, protons, we think they live forever, but what if they only live for, well, almost forever? Let's say they will break apart and decay into something else. It just takes a really long time for this to happen. And so people thought, hey, great, this is a good theory. Let's go see if we can detect this. Let's go build an experiment and hope we can see protons decay. So in particular, in the mid-80s, there was a professor at the University of Minnesota, Professor Marvin Marshak. He was in northern Minnesota on what I believe was an anniversary vacation with his wife. And they went to the state park up there. It's called the Sudan Mine State Park. It is a defunct iron mine shut down in like the 60s. he was there enjoying his time with his wife for their anniversary and had an idea of, hey, this would be a great place to put a physics experiment. You know, glad his mind is in the right spot, right? So he built a detector called this, now, it's now labeled the Sudan-1 proton decay experiment. And he put this detector on just some old cavern that the miners had dug and left empty. And he didn't see anything. However, it was such a good idea that he convinced the powers that be, aka the people who give you money to build experiments, that they should give him more money to build a bigger experiment in Sudan. And so this became the birth of the Sudan Underground Laboratory. So it actually is this kind of a schematic of it. And think about each one of the solid things you see here are actually, caverns in the rock. So it's kind of a reverse picture. Everything that's see-through is actually rock. Everything that you see here is a cavern in the rock. This kind of slanted line that comes down from the top, this is actually the elevator. And down the elevator, these tunnels over here, these are all the tunnels that the miners had dug. And people liked the idea of doing physics underground so much that after the Sudan-1 experiment happened, they actually dug 2 new really big caverns. And these 2 new caverns are what turns into the science laboratory. And if everyone always asks, so you get off the elevator and there's a nice sign for all the tourists. You are 2,341 feet below the surface. So that's how deep underground we are with a whole bunch of limestone rock above us. So there's 2 caverns. And the blue cavern here is where the Minos experiment lives. So Minos is this hexagon thing. This is looking at from dead on. It's actually a cylinder. So if the hexagon is about this big, it's about that long. So it's a really big hunk of iron, actually. That's what's made out here. And they look for neutrinos. So Dominic's experiment NOVA, which you probably talked about 2 weeks ago, is the kind of successor to Minos. Same idea, just kind of different location, different materials. His is made out of plastic, this is made out of iron. And you can maybe tell, but you can see some staircases over here. So you see that Minos is actually 4 stories tall. So it's a really big hunk of iron. And next to it, there's, this is looking head on, there's actually a wall over here. See the wall of the cavern. So if we kind of take our camera and pan it to the right, you see a big piece of art. So there's a law in Minnesota that if you build a public facility using a state bonding bill money, that 0.5% of the cost has to go to public art. It's a law. We just built a new physics building on campus, and we had to build some art too. So Sudan Mine was no exception. So they brought an artist in to build a mural. This is on this side of the rock. It is also 3 stories tall. He sat there in a harness and painted directly onto the rock. We have a big projector that projected it onto the rock for him. And pretty much it's a mural that kind of tries to explain the history of the neutrino. You can't see the details. I don't know all the details, but an artist's interpretation of the history of the neutrino, which means it's kind of fanciful and hard to understand because it's modern art. But anyway, there's a big piece of art that you'll see if you go on tour, say, for example. All right, so this was all in this blue cavern over here. So let's kind of shift over to another cavern that's the same size. It's the gray one. And the gray cavern was built to house the Sudan-2 proton decay experiment. So Marshak first built Sudan-1, didn't see anything, but it was a good enough idea. They said, here's a bunch more money, make it bigger. So they made it bigger. This is 1 kiloton of iron sitting there, and they were hoping to see protons decay. They still didn't see anything. Actually, no one's ever seen this. They aren't the only ones who tried to do this. No one's ever seen protons decay, which is made a lot of theorists very sad because they really liked the theory that totally protons should decay. So then they just made up a band-aid and said, hey, we have this nice theory. Oh, well, let's put a band-aid on and say, hey, if this is also true, then protons won't decay. So they kind of had to bow to the pressure of the experimentalists and put a band-aid on their theory. Well, so the Sudan-2 didn't see anything. So it shut down probably, I don't know, mid-90s, 2000, somewhere in there. And this is what that same space looks like now. So it's mostly empty, actually. This is where Sudan-2 sat. There's a couple other smaller experiments in there now. But this cavern wasn't completely a loss, because right next door to where the Sudan-2 stuff was is where CDMS, my experiment, is. So we went in next door and said, hey, this is really great space. You have lots of open space now. Let's put our experiment. And so this is kind of a not so great picture, because apparently we don't have any good ones. I don't know, I can find any, of the top of our experiment. So let's kind of talk about what I actually do now in my experiment. No questions? I'm not silent. Ask them. Oh, yes.
What's the reason behind putting the experiment so deep below the ground?
Sure. So we are looking for rare events. So rare events is going to be like one event every couple of years, maybe 1, 2 events. I don't know. And there is a lot of junk in the atmosphere. So there's a lot of stray dust in space, just a lot of hydrogen flying around, and when that dust hits the atmosphere of the Earth, it makes a whole bunch of particles and junk. And so we go underground because the Earth then shields us from all that extra stuff that comes from space. It's happening and going through us all the time, but it's not really a health hazard. But you might hear some people say that, oh, if you fly more, you'll get a higher exposure to radiation. This is kind of the stuff in the atmosphere. The further down into the atmosphere of the Earth you are, the less stuff you get exposed to that's coming from space. And so it's kind of, instead of looking for 2 events in, like 7 billion events, we'll look for 2 events in a couple of thousand or so. And just kind of reduce the number of other stuff that our detector can see. All right. So CDMS is a collaboration of a bunch of different universities. Here's a picture we took in January when we all got together. But there's maybe about 20 different universities listed down here. University of Minnesota's over there, but we have stuff like MIT, Stanford, University of California, Berkeley. So, there's a lot of these really well-known schools in the country. All have members in our collaboration. And so,
Ed, did you have a question too?
Yeah, what would they expect protons to decay?
So that would be a muon and a neutrino, I believe, if I remember correctly. Part of the thing that's tricky about that is no one's ever seen something where, like, what's called baryons, so stuff made of quarks completely decays into stuff that are not made of quarks. And so that's kind of, there's a theoretical idea that maybe this isn't possible, and maybe for some reason quarks don't like to go to other stuff. But yeah, it would go to like a muon, which is a heavy electron, and a neutrino, if it happened. I mean, if someone saw it, that'd actually be pretty big news.
What does CDMS stand for? Did you say earlier? Oh, okay.
Next slide. So I'll get to that. Any others? All right, so CDMS stands for the Cryogenic Dark Matter Search. We are not as creative with our acronyms as other people are. It's not actually working. But anyway, so we are a dark matter direct detection experiment. And so the cryogenic part here means we're operating at really cold temperatures. So in particular, we are 40 millikelvin above absolute zero. So this is like 60 times colder than outer space.
How do you get that cold?
Very carefully. This is liquid nitrogen, liquid helium, superfluid liquid helium, and evaporation, like your sweat. Like, sweat evaporates off and it cools you down. We kind of evaporate one kind of superhelium off the other kind of superhelium, and that actually lowers it the last little bit down. It's hard. You spend a lot of effort to keep it that cold, and it's really expensive too. So liquid helium is also what keeps MRI machines going. So an MRI machine has a giant supermagnet in it, superconductor, which makes a big magnet. This only happens when you're at a cold temperature, and so hospitals spend a lot of money on helium, liquid helium, and we've actually run into issues where there's only a couple of really big manufacturers of liquid helium in the country, and for like a year ago, for some reason, 2 of them both shut down for a month. Like they were both doing maintenance at the same time. And so there's actually a big shortage of helium, and of course when you think about, physics experiment in the bottom of an old mine, MRI machines at hospitals. You know, you can guess who they're going to supply to first, right? So we had to pay like 3 times more for our liquid helium because there was this kind of national shortage. Because it's the same stuff that happens.
Isn't this experiment done in like a colder place then? Like they keep computer servers in Siberia, or can scientists not hang out in Siberia?
Because the difference in temperature between here and Siberia is insignificant compared to how cold this is.
Yeah.
Yeah, we had at one point someone thought we went underground because they thought it was colder underground. It's actually 60 degrees all year round underground, doesn't change, in case you're wondering. But you know, so it's kind of, you know, just this common idea of, but the change in temperature, you know, say here in Siberia, maybe it's like 20 degrees. To get this cold, this is a change of like negative 300 degrees. So it's just not, doesn't make that much of a difference. All right. All right. So then we operate really cold, and I'll explain why we need to do that in 2 slides away, I think. But what we use as our actual detectors, I talked about Nova is made out of a bunch of plastic, Minos is a bunch of iron, so is Sudan too. We actually have a detector made out of germanium and silicon. So silicon, you hear a lot about, that goes into a lot of computer components, and then germanium is another rare earth that a lot of ceramics are made of. And we actually have...
If there was a germanium shortage, would it go to the ceramics industry first?
Possibly. We actually have people who grow it for us, so it's not like there's a big manufacturer out there that we buy from because we need it really pure. So we actually have, there's actually whole science labs dedicated to just growing our germanium for us.
How do you grow germanium?
I don't actually know how many, to be honest.
It just shows up, man.
Yeah. Give the same answer, probably very carefully. So we have kind of a history as well. We are started in '98 in Stanford. We moved to Sudan early 2000s, maybe like 2003. And each kind of way we go, we got more germanium. So we started off with about 1.1 1/4 kilograms total. So we're not that big. We went up then to about almost 6 kilograms. We are currently at this stage where we have about 10 kilograms, and each one of our detectors has kind of gotten bigger and more advanced. And we are very excited that we found out about a month ago that we get to build a bigger one. We submitted funding for an upgrade and they actually said, yeah, sure, we like it, we'll pay for it. And so we're actually going to move to a different lab, which is in Sudbury, Canada. It is over twice as deep as Sudan is. And we're going to increase our size again to about 50 kilograms, split between germanium and silicon. And so to give you a better picture, this is what each one of our individual detectors look like. So the first kind of iterations use this guy over here. So it's about 3 inches across and 1 centimeter thick. It's pretty much a shiny hockey puck. We then got bigger. So the guy shown up on the right-hand side, it's the same 3-inch diameter, but now it's 1 inch thick instead of a centimeter thick. These are the detectors that we have up north right now, running them. And then the one we're going to build in Canada is the one in the lower corner, which is hard to tell, but this is even thicker and wider. So we have more detectors, and each one of those detectors gets progressively larger. And so the way these guys work, to give you a little bit of a general idea about why we use or how we use these guys. The idea is, okay, we need to detect individual particles hitting our detector. Hopefully we can detect individual dark matter hitting our detector. So the idea is that if you have, we have a little cartoon over here. Sorry, it's black, hard to see. But this is a bunch of atoms lined up. So this is the germanium crystal. You have the green and red stuff in the middle of the protons and the neutrons. And then you have these electrons going around outside. It's a cartoon, as I said, but it gets the idea done. So if you have a particle that interacts with light, so not dark matter, I know that was one of our key categories, so this is stuff that is not dark matter, they're going to come in and they see some nuclei, protons. They have a positive electric charge. And then they're going to see a whole lot of electrons around them which have negative charges. And so they are going to see the electrons first. I mean, there's like 70 electrons per every nucleus. So there's more electrons, they come in, they're going to hit the electrons. And so they hit the electrons and they knock, they kind of kick the electron off the atom. And we apply an electric field across the detector, and so when an electron gets kicked off an atom, it actually travels along the electric field and we collect it. So we kind of count how much charge a particle made. And so we count the charge. So that's one way that we look at it. So now let's take something that's somewhat more interesting. Let's say something that doesn't interact with light, like our WIMP, our dark matter. This also counts for neutrons, another kind of normal particle that would look the same to us. They come in, they don't have an electric charge, so they don't care about the electrons. They see the nucleus, and these guys interact through the nuclear forces. So they will only see the nucleus. They go in, they smack the nucleus, and the nucleus shakes. And we want to be able to detect how much it shakes, how much vibration this nucleus has. And this is why we need to operate so cold. Because just at room temperature, the atoms and everything, the tables, chairs, us, whatever, they're just shaking on their own, some amount. They shake no matter what temperature you're at. But as you get colder, they shake less and less and less and less. And so if we want to see, the vibration from hitting one of those atoms, well, if we're at room temperature and you hit them, we won't be able to see it because they're moving too much on their own. But if you cool down to almost absolute zero, they're shaking little, and so when they get hit, you can actually see them getting hit by something else. So that's why we're so cold, because we have to be able to see these vibrations. And so we collect charge, electrons pretty much, and we collect the amount of vibration that an atom makes. And then we compare the two. So here's just a kind of a brief graph of how we compare it. The idea is that we look at the charge energy that we saw divided by the charge plus vibration energy. And so if you hit an electron, you didn't hit the nucleus. So if you interact with light, if you're a photon or an electron, you would sit at 1 up here. So all the guys in blue up here are these kind of electron recoiling background events, gammas, electrons, etc. Whereas if you hit the nucleus, if you're a WIMP or a neutron, if you don't care about the electrons, you would shake vibrations, and so we'd see more vibrational energy than we do charge energy. And so you sit lower down here at maybe about 1/3. So you see these kind of green bands. So stuff inside these green bands is what's going to look like a dark matter to us. So we do our experiment, we sit there for a long time, and then we can count how many dots are in this area. And again, that's really all we do. But it takes a lot of work to get there.
How is it that some of the yield data points are above 1?
Statistics. So it's just kind of the, if you measure this table 10 times in a row, you're probably not going to get the same answer 10 times. If you go down, you'll have slightly different answers, or if you measure it and then the next guy comes around and measures it, you're going to get slightly different ideas. And there's just kind of this natural uncertainty in measurements, which just comes from statistics. And so you kind of have to deal with averages. And this is just kind of like a statistical fluctuation of this guy happened to measure it longer than this, the other guy. Okay. So it's just kind of any experiment you do, there's kind of this natural width of just, if you make better experiments, this should get shrinker and shrink down onto 1. But it's just kind of a factor of how good actually is your experiment. Another guy is.
Yeah, how do you know the green band is where you expect it to appear?
Because we put a californium atom next to our detector, and a californium atom radioactively decays and spits off neutrons. And neutrons is the other particle I said that would look like a WIMP. They don't care about the electrons, so we calibrate it using neutrons. We say, where do all these neutrons that we know should be there, because we stuck a radioactive source next to it, and say, where do they live? And then we kind of use that as a guide to say, okay, this is where we expect to see the dark matter.
What's your units?
So the units on the bottom is in kilo electron volts.
Yeah.
So it's energy pretty much. It's how much energy was in the recoil. Electron volts is just another unit of energy. really small amounts. But
So a lot of people are doing studies with CMS data and building mass plots. And so you're seeing a lot of GeV, MeV, those are the same except for different orders of magnitude.
Yeah, so this is 10 to the 3 electron volts. GeV is 10 to the 9 electron volts.
But your ionization yield.
Ionization yield actually is unitless because it's a ratio of two energies. It's the ratio of the charge energy divided by charge plus phonon energy. So it's kind of energy over energy. So it actually doesn't have any yields. Yeah.
Why do you guys use germanium in particular?
So because when we started doing this, late 1990s, all the good theorists told us that dark matter should be, I don't know, maybe 30 to 60 GeV in mass. And that is precisely how massive a germanium nucleus is. So we kind of picked our target nucleus to match the mass of dark matter, because if you just do a simple elastic scatter, you take pool ball, you hit another pool ball with it, well, it goes the furthest when they're the same size. Like you hit a bowling ball onto a golf ball, or it's a better question, when you throw a golf ball at a bowling ball, it doesn't go very far. Throw a bowling ball at another bowling ball, it might be fun and it'll go farther. So the idea is that we want to make it the same size as what we think dark matter is going to be. And again, this is just what the theorists told us in the late 90s. They might tell us something differently now because we haven't seen it yet after 15 years. But it was kind of a choice made then, and we've gotten really good at it, so we've stuck with it. You can do other things. The other really popular element right now is xenon. So xenon is a noble gas. They just make a giant vat of xenon gas. And they kind of look at the same things. They look at the electrons knocked off it, and then they look at scintillating light. Just another idea. It's a different experiment. They're actually really good at it. And they can make it a lot bigger than we can actually. But there are ideas of different targets to use. This is just the one that I guess they're now really old guys in the collaboration thought up of in the late 90s.
Does the detector give you real-time data, or do you need to let it run undisturbed for a certain amount of time to get the data?
Both. So we do get data in real time, and we kind of do basic analysis on it at that level. So we kind of run it in chunks of about 3 hours. And so as each 3-hour chunk comes in, someone looks at the data kind of at the top level analysis. Does this data look good or not? Sometimes they throw it out right then. Most of the time they keep it. But then after we collect enough of it, we kind of do a more in-depth processing and analysis of the data. So we kind of do some data quality right away, and then maybe after a year or so we'll do a big chunk of it and look really in depth, and that's what gives us the actual physics results is when we do that. And mainly one real difference is to do that in depth you have to do a lot more extra computing on it, and that takes a lot of effort, so we can't really do that in lifetime. We just kind of do it in one big chunk every so often. All right, I'm kind of getting close on time, but I really want to make sure I talk about this guy. There's kind of talk about some other, one thing that makes this hard is, as I said, on the surface, there's a whole lot of extra stuff flying around, so we want to avoid that. And this is kind of the idea that there are going to be background events that are hitting our detector all the time that aren't dark matter. So we need to be able to decide what is or what isn't dark matter. So at the end of it, we kind of use this yield differentiation, bad guys up here, good dark matter down here. But we can only do that because we have already only, a million, maybe a million events. And this is, we have to, if we didn't have any sort of background rejection, we would have billions of events. So it'd be a little bit more difficult. And if you talk to anyone who works on the LHC, you'll hear just how difficult having billions upon billions upon billions of events are, because that's how much they make every day when they're running. So what we need to do is try to block out as many other sources of events as we can, just to make our lives manageable in the analysis. So one of them is the cosmic rays. So this is the stuff coming from space I mentioned. This is why we go underground. And then the other fun one that I've spent a lot of time thinking about is what I call ambient radioactivity. So the idea here is that anything that came out of the ground has some amount of radioactive material. And I mean anything. Tables, the ground, the walls, you name it. Including bananas. So bananas actually are very radioactive in a sense. They have 15 radioactive decays per second for a single banana. This is really low, so that's why you can eat bananas and not have to worry about it. You know, you get more coming from space than you do from bananas. But to give them a sense, if we were to put a banana next to our experiment, it's 10,000 times too radioactive for our experiment. If we put a banana there, we would never, ever, ever hope to see dark matter, because it would just be decaying so much. So this is the idea that even normal things that we don't think about in everyday life are, you know, too radioactive to see dark matter through. So this is how we kind of build our detector to block stuff out. I guess this is a picture showing going underground reduces the stuff coming from space. I kind of already mentioned that. I'll skip that one. But then otherwise, we kind of build our experiment to block out, you know, all the radiation coming from normal everyday stuff. So this is it's a simulation picture, but this is kind of a cross section of our actual experiment. So we first have the stuff in white is plastic, just polyethylene plastic. And we have this in there because plastic is actually really good for stopping neutrons. And neutrons look like our dark matter. You know, we use them to kind of fake dark matter signals to figure out where that band should be. So we really want to make sure that no neutrons get through. In particular, these are going to be neutrons just decaying from the rock, for example, or the steel that we built the platform out of. They're going to decay and give us neutrons. So that's what the, I guess I have little arrows here, that's what the white is. So we have, you know, like, maybe about 20 inches, you know, in any direction of plastic just to block out these neutrons. We also have in red here, this is lead. So lead is really heavy and has a lot of electrons in it. And this is what blocks out just kind of, you know, photons or other electrons, other radioactive, you know, stuff that interacts electromagnetically will get stopped by the lead. This is somewhat of a problem though, because lead itself is one of the more radioactively known materials. Kind of chicken and the egg problem. You want to block some stuff, but you block it, but make more. Ideally, you make less. But we have there's two layers here, and one of them is a dark red. It's probably really hard to see. That's what this second little arrow is. So this interesting story is that this lead in this inner layer, it is only, you know, just shy of 2 inches thick. This is lead from an ancient Roman battleship that sunk and sat at the bottom of the Mediterranean Ocean for 2,000 years. So the idea is that the longer something is removed from the earth, you know, you mine something, and if you go set it in a corner for a really long time, its natural radioactivity will decay away. In this case, it sat at the bottom of the Mediterranean Ocean for 2,000 years, so it is significantly less radioactive than normal lead is. And we only got this because one of the head honchos in the group is French. And the Italians who found the ship liked the other European because he was French, and they sold it to him, and he brought it to America, and we built it here. I'll be honest, you probably couldn't do this today. I mean, I'm sure there's historical regulations about doing something else. But it didn't exist 15 years ago, so we got to do it. And no one's asked us to give it back. All right, and then I'll just show some pictures of, quickly, out of time pretty much. But so this is actually assembling our experiment. This big white slab is the plastic I talked about. Inside the kind of shiny foil is a bunch of copper cans. These are cryostats. There are a bunch of 6 cans inside of each other. Each one is somewhat colder than the last. So this is where your liquid nitrogen comes in, and then your liquid helium, and then super liquid helium, etc. Fancy stuff that I am not an expert in. And then this is kind of looking from above, so it's a cylinder, and this is looking from above, and they're actually, there's multiple layers of copper here, and you can kind of see some hexagons down here in the bottom. And these are actually the detectors. There's kind of 6 of them in a stack, and we have 5 stacks sitting there. And you can see I'm putting in one of the stacks here. This is from a few years ago, and we installed the current stuff that's up there. I it's kind of 6 o'clock, so I think a picture of the experiment may be a good place to stop. I have some more stuff talking about our results, but that's just kind of how, what we're trying to see, how it works more or less when we do it, you know, what our experiment looks like, what it's built down of. But give me some more questions. They're good questions, so why don't we have them?
How big is the space you need to cool?
The space we cool is probably, I don't know, about that big. The idea is that each one of these is a vacuum though. So you shouldn't, you know, if this one's temperature, say 1, and the guy outside is at temperature 2, well there's a vacuum, there's no way for them to kind of interact with each other. So once you get it down there, it's easier to keep it at that level. Just because it's, you know, a vacuum around it.
Like, briefly, what are your results?
I can summarize that in one plot. Yeah, here you go. So, the way these plots work is on the bottom. This is the hypothetical mass of the dark matter. So this is in units of GeV per c squared. So as I was mentioning, if you're looking at CMS data, that's the same units of mass that they talk about. The Higgs boson they found last year is at 127 GeV squared, somewhere around there. A proton is about 1 GeV squared down over here. And so we don't know what it is, we don't know what its mass is, so we just kind of look at over a broad range. This is from, you know, like half of a GeV up to 10,000 GeV squared, so we really don't know the mass. And then on the right-hand side here is pretty much a, you know, probability that it'll actually interact. So if you have a high probability, you're going to be way up here, low probability down here. Is this in the middle of this, or? Okay. So the idea is that these lines are each from a different experiment, and they have said that they think that anything above their line can't be true. So the best result in the world right now is this green line. It's from Lux. This is one of those big vat of liquid xenon I talked about. They're located in South Dakota, actually. They say that every combination of mass of the particle and probability it's going to interact up here can't be possible. Because they say if this were up here, we would have seen events. We would have seen dark matter already if it were up here. And the state of the entire field across the whole world is kind of confused. Because first of all the best theories say dark matter should be down over here. So this is why we picked germanium, why they picked xenon, because everyone thinks it should be over here. However, over the last 5 years or so, there have been a handful of experiments who had some events. So each one of these kind of closed off regions, so the magenta one's here, a brown one over here, a blue one here, these are all experiments that actually saw some events. And so what they say is, well, if these events were dark matter, it would have to live up here. So it's kind of the state of confusion. The theories say it should be down here. Some experiments, including CDMS, one of these guys is a CDMS result from 2 years ago, think maybe it's up here, but as you can tell, these regions are kind of inside some of the lines. So experiment 1 says, hey, we saw some events, maybe it's here. Experiment 2 says, no, if it were there, we would have seen it too, and we don't see it. So it's a little bit of contention between the theorists and the experimentalists, and then in between the experiments themselves. And this pretty much just means that we need to do a better job, particularly in this region, because most of these, I can say one in particular, this pink one here, it's an experiment in Europe called CREST. They had these events, and then about 3 years later, they said, we're pretty sure that the clamps we used were radioactive. So we think these were, they tested all their parts, and they figured out these guys are extra radioactive, so our events probably came from that. So it means these guys, this is a fake. Brown guys called DAMA, they have seen a signal for 12 years now. It's a really strong signal too. The problem is that no one else sees it, and they are very closed-lipped about their data. They won't let anyone else see it. If you ask them questions, they won't respond. They rarely go to conferences. They'll go to a conference once every couple years, show another really good-looking result, but then they won't let you talk about it. So no one trusts them. Let's just put it that way. They're over in Italy, and no one trusts them.
Wait, if you show up at their lab, what will they do?
They won't give you a tour. They're underneath the mountain. They won't give you a tour. But anyways, there's not a complete
Sending people.
There's a really little one here that's yellow, corresponds to this cogent guy. This is run by a guy named Juan Collar. He's at the University of Chicago. He's actually very smart. He's a very brilliant man. He just has a very abrasive personality. And he will tell you how everyone else is doing something wrong except for him. So people have a hard time with him as well. I mean, it's just kind of this, you know, there's a story behind each one of those things and kind of reasons why some people don't believe them at all. And say, this green guy must be right. And this is why we actually were told to fund our upgrade, because we're going to be really good over in this area. Hey, it's worse now. We're going to be really good over here in our upgrade. And that's why they wanted us to build an upgrade to clean up that mess.
How will you know you found it?
So one, you see a lot of events. If you see a ton of events and you spend a lot of thought to make sure they're not from radioactive clamps, you have to convince yourself that you didn't make a mistake first. I mean, this is how real science happens. You know, you see a result, the first thing you have to do is convince yourself you didn't make a mistake. Everyone does this. You may have heard a couple years ago, there's a kind of a well-known example. There's an experiment also in Italy who thought neutrinos went faster than the speed of light. They didn't check enough because they had a loose cable. That's ended up what the difference was. One of their cables was not tightened enough, and this had a little tiny delay, and that delay was enough to fool them. So they published this result, and then a couple months later, they managed to figure out where they made a mistake. So that's kind of what you don't want to do. You want to find that first. So you hope you didn't make a mistake, and then, well, you kind of have to play a waiting game. You saw a result. Okay, first of all, can you reproduce it? If you go do the same experiment, do you see that result again? That's what DAMA claims they can do. They've been doing it for 10 years. So that's what they say is their really good strength, that yes, they get a result, they see it every time they do the experiment. But that could just mean your experiment's flawed. So you also have to wait to see, can someone else see the result? Do they see it in the same spots? This is kind of a complementarity of, you may be the first one to see it, but until more than one group sees it, the scientific community isn't really going to accept it. So it's kind of, you get a result, and if you think it's right, you put it out there, and then you just kind of, science is, you kind of batter back and forth until everyone kind of, there's an accepted view, and enough experiments see it, that's kind of an indication that, yeah, it must be true. And then whoever found it first gets Nobel Prize. But yeah, I mean, it's hard, and that's kind of just the nature of how science works, I guess. Another good example is in the 80s, someone thought they saw a magnetic monopole. To someone else who happens to be in our experiment. He thought it was a great result. It was another rare event search. They found it. They couldn't find any mistake they had made, but no one's ever seen it since, including them. They got a lot of money to build another one, a better one, and see if they can see it again. They never saw it again. No one else ever saw it again, so it just kind of got
What did they say they saw?
magnetic monopole,
Oh.
which is something that shouldn't exist theoretically, or whatnot. So it's kind of this idea of they thought they had a good result, but no one else could ever see it. So people now ignore it, and they still think they don't exist. They made a mistake. They just couldn't find a mistake.
All right. Well, if you have additional questions, maybe you'll have, if you wouldn't mind sticking around for a few more minutes. We could have some people, I know some people are going to have to go. And yeah, Mark, there's some more pizza for Mark to be able to have. Is there any left back there? I know he had a piece or two to begin with. I think there is.
Yeah. We're good.
So save a couple for him.
Approximately
Otherwise,
a whole pizza left.
eat the rest up. Same with the pop. I don't want any of that pop. Anything that's left over, I'm going to throw down the drain. So take it with you if you want to. If you can make sure to throw away your trash on the way out. Blue chairs, if I can get some people to stack blue chairs over here, I got to take them to a different room. And if somebody wouldn't mind wiping up any sticky spots on tables with this, we're going to grab this real quick. And if you have questions for Mark, you can come up here and chat with me. Right? Let's give him another round of applause.
Jane, can you remind people about tomorrow's timing?
Yes, that's the other thing. So tomorrow, especially for those who were here last week doing the analysis of the data, tomorrow is the day that we're going to chat with 2 other groups from around the country who are doing the same investigation with that CMS data. And we have a woman from England who's going to be moderating our video conference. Summer is her name. And so we're going to talk to her about our result. This would be especially helpful for those who are doing the study with that, what's the name of the software that we downloaded? It was for the Atlas data, but the Delphi, no, not Delphi. Atlantis? No. Atlantis? Is that what it is? Okay, there's so many different viewers. Atlantis view, yeah. So especially for those who are analyzing that one, it's really helpful. So,
3 o'clock tomorrow?
By 3 o'clock. It'll be good to be here before so we can do a little preliminary. Yeah. Some more pizza. And if you have questions.